you may know, this is not really my field of research, but it's something I've become very interested in recently, and talking about it with Lillian, and I really thank her for inviting me to speak on this because it's very exciting to learn this material, and I'm happy to share what I've learned with you all. So let me start by motivating this with Hilbert's 12th problem. So we start very basic. So a number is called algebraic if it's the root of a polynomial with rational coefficients, and the set of all algebraic numbers forms a field. Now, Hilbert's 7th problem in his very famous list of 23 problems stated at the 1900 ICM was the following questions in the field that we would now call transcendental number theory, which is if we start with an algebraic number that's not 0 or 1, and we raise it to an algebraic power that's not rational, then is that resulting value of a to the b, is that necessarily transcendental? For example, square root of 2 to the power of square root of 2, is that necessarily a transcendental number, or does that have a hope of being algebraic? So a way of rephrasing this is if you take the equation a to the b equals c and you apply the logarithm, then you get b log a equals log c. So what you're asking is these two logarithms of algebraic numbers, log a and log c, is it possible for them to be linearly dependent over q bar without being linearly dependent over q? Okay, so that's the question. And so here is David Hilbert. Right. So the answer to this question is yes. It was proved independently by Gelfond in 1934 and Schneider in 1935. So as I stated in the previous slide, another way of stating Hilbert's problem is that if you take two algebraic numbers and you take their logarithms, and they're linearly dependent over q bar, then they're actually linearly dependent over q. Okay, and so I should be a little bit clear because log is sort of a multi-valued function. Log means any log, so any number. So log a stands for any number x such that the exponential of that number x is equal to a. Okay, so Baker's theorem, which was not proven until 3 decades later, is a generalization of this fact to n algebraic numbers. So Baker's theorem is that if you have n algebraic numbers whose logarithms are linearly independent over q, then in fact they're linearly independent over q bar. Okay. And the focus of today's lecture is going to be on proving Baker's theorem. So here are Gelfond and Schneider, who proved positive answer to Hilbert's question in the 30s, and here's a picture of Alan Baker, who won the Fields Medal for this work. Okay, so this is restating Baker's theorem. If I have algebraic numbers whose logarithms are linearly independent over q, then they're actually linearly independent over q bar. So I should mention that Baker's theorem is actually stronger in 2 ways. One is that you can throw 1 into the set of numbers that are linearly independent. So if you have elements that are logarithms that are linearly independent over q, then in fact their logarithms together with the number 1 are linearly independent over q bar. That's useful for some applications. And maybe even more importantly is that the theorem is actually effective. That is, you get a lower bound on the quantity beta 0 plus beta 1 times log alpha 1 all the way up to beta n times log alpha n for any algebraic numbers beta I with some explicit sort of lower bound. So there's a bound from how, it's not just that it's non-zero, it's kind of bounded away from 0 by some effective amount that you can write. And I'm not going to do that. I'm not going to prove either of these things because it just gets a little bit more complicated. In fact, I'm going to make an even further simplification. I'm not even going to prove this. This is what usually people sort of refer to as this qualitative thing as Baker's theorem, though this explicit effective version is very useful. I'm going to prove something even slightly weaker. Sure, I have trouble advancing these. There we go. We'll prove something slightly weaker, which is I'm going to increase my assumptions, which is I'm going to assume that not just that log alpha 1 through log alpha n are linearly independent over q. I'm going to assume that those numbers together with 2 pi I are linearly independent over q. And then I'm going to make the sort of weakest assumption, weakest conclusion of the various statements I've considered so far, which is that log alpha 1 through log alpha n are linearly dependent over q bar. So I'm sort of giving myself a little bit extra. I should say that all of the results that I mentioned are proven in the same way. That is, getting rid of this 2 pi I is not a big deal. Making the effective version is not a big deal. Just makes all the notation and arguments slightly more complicated. And in a presentation like this, there's no real value in doing that, instead of just giving you the main ideas behind Baker's sort of amazing proof about why this result is true. So let me just explain where the 2 pi I comes from. The conclusion we're going to make from the assumption, so we're going to kind of prove the contrapositive of this. So we're going to assume that log alpha 1 through log alpha n are linearly dependent over q bar, and then we're going to produce a linear dependence of these numbers over q. And how are we going to do that? Well, we're going to do it without the logarithms. In other words, we're going to assume that if log alpha 1 through log alpha n are linearly dependent over q bar, then in fact, there's an expression that's alpha 1 to the lambda 1 times alpha 2 to the lambda 2 all the way to alpha n to the lambda n equals 1, where the lambda i's are integers that are not all 0. Okay, then just by applying the logarithm to this equation, you get exactly the sum of lambda I log alpha n, but you don't necessarily get 0. You get that it's equal to some integer multiple of 2 pi I. And so that's why we need to include that in our assumption that they're linearly dependent over q with 2 pi I in there. So that's the explanation. Again, you can get rid of this if you're more careful. Okay, so that's sort of the goal. So it's a long proof, so I'm probably not going to get through all of it today. I'll do as much as I can, and kind of next time, do the end of the proof and sort of remind you what we did today. Maybe I'll get through, we'll see. Okay. Okay, and so I'm going to give you sort of an outline of the proof at the beginning. It's going to be a little bit vague, and then I'll do the proof, and then I'll do this basically outline again and summarize it, and I hope that once we've seen it, then the big steps become clear. So the first big step is how do you show that you have an expression like this, that product of alpha I to lambda I equals 1. So one thing I can say is that when I first heard the statement of this theorem, I mean, is very naive. I thought that the way that you prove it is you say, okay, I start with a linear dependence over q bar. Then you kind of want to show that directly from that linear dependence that somehow the coefficients have to be rational, or that you can kind of take a basis for the coefficients over the rationals, and then each sub expression you get like that's actually equal to 0. So somehow get the linear dependence over q directly from the linear dependence over q bar, which you're given. That's kind of a natural thing to try to do. But in fact, that turns out to not at all be the way that the proof works. So you start with a linear dependence over q bar, and then you use a whole system of other techniques, in particular, the use of auxiliary polynomials, which is the theme of this conference, in order to show somehow that there exists some other, maybe completely different lambda 1 through lambda n, such that the sum of lambda I log alpha I is equal to 0. Okay, so that's one thing that's first to note, is that the lambda i's aren't deduced directly from the beta i's. There's a very indirect procedure by which you show the lambda i's exist. And the key concept here is the use of auxiliary polynomials. We will show that it suffices to prove that there exists a polynomial satisfying certain properties, having lots of roots that are of a specific form, and that the existence of a polynomial with roots of that form implies the existence of lambda I, giving this dependence. Okay, so that's one thing to note, is that auxiliary polynomials are the crux of this proof. Okay. Okay, so how do we construct such a polynomial? So 2, 3, and 4 kind of all go together in reality, but let me try to separate them a little bit. So Baker first starts by saying, okay, well, how do I construct this auxiliary polynomial? And there's the very classical technique due to Siegel that basically boils down to the pigeonhole principle, which sometimes is called the box principle, Dirichlet's box principle. There's lots of different names for it, but basically it's the pigeonhole principle. You express the existence of your polynomial, as, just like we saw in the last lecture, as solution to a bunch of linear equations. And then you show somehow that there exist coefficients that satisfy these linear equations. I'll explain that in a bit. And it boils down to the pigeonhole principle. That is, there's too many pigeons to put in the number of boxes that you have without two of them falling into the same box. Now, when you do that, you don't get enough roots. You can't do something so simple and get sort of a polynomial with so many roots that it implies the existence of this linear dependence of sum of lambda I log alpha I. In fact, you can see that you can't even without doing the arguments, because the whole point is a parameter counting, right? The pigeonhole principle, the reason it works is they're parameter counting in saying that you have sort of more pigeons than you have holes. So you use the parameter counting to show that you have the polynomial. You can't then use parameter counting on the polynomial to show that it implies something that doesn't always hold, right? So you know that you couldn't possibly get the polynomial you wanted for the step part one to work just by using pigeonhole. But, and this is Baker's amazing idea, is you construct a polynomial that has not just a bunch of roots using the pigeonhole principle, but he shows that what's very useful is if you make its derivatives have lots of roots too. And then, so 3 and 4 really do go together here. So let me actually say 4 first. So once you have roots of the derivative, he uses a complex analytic tool, which is some generalization of the Schwarz Lemma, which says that when you have a function and its derivatives with lots of roots, that bounds the magnitude of the function. And now this is where you use algebraicity. So we have sort of the coefficients. This is why the coefficients, the beta i's being algebraic, is very important, which is that when you have a function that's very small on algebraic parameters, then it somehow has to be 0. Okay, so algebraic numbers, so this is why I call the discreteness of the algebraic numbers. Algebraic numbers can't be too close to 0. Most simply, integers can't be close to 0. If I have an integer, an honest integer, a rational integer, it's an integer, and its absolute value is less than 1, then it has to be 0. And it's really just a generalization of that concept that says that once we've bounded this function using complex analytic techniques, and we specialize it to algebraic parameters, if it's too small, then it has to be 0. And so that's how we get more zeros to our original function, so that this original pigeonhole principle wasn't giving us enough zeros to do what we wanted. We then use analytic techniques to bound the size, and then use the discreteness of the algebraic integers to say that if they're that small, they have to be 0. So now we get more zeros, and then you produce your polynomial. And in fact, this whole procedure gets iterated. It's not just one time that you get more zeros. And then with those extra zeros, then you say, oh, I have even more. The Schwarz's lemma is even stronger. It's giving me more of a small bound. That more of a small, that even smaller bound then gives you even more zeros. And you keep iterating until you get enough zeros. So that kind of extrapolation method was really what Baker's idea that he brought to this this result, which was really kind of groundbreaking at the time. Okay. All right. So now let me say in detail about this method of producing an auxiliary polynomial that allows you to conclude what we want, which is the existence of the lambda I such that alpha 1 to the lambda 1 ... alpha n to the lambda n, that product is equal to 1 for some integers lambda I that are not all 0. Okay, so the auxiliary polynomial that we're going to construct is a polynomial. So I'm going to call it degree L, and I have a different definition of degree than in the previous talk. So my degree is just going to be the maximal exponent of any single variable rather than the sum of the exponents. So I'm going to have a polynomial where each xi is raised at the most Lth power, and the coefficients are actually just going to be integers, rational integers. I'm going to have some bound on them in a moment. But let's just say I produce any non-zero polynomial of degree L, okay, with the property that when I plug in alpha 1 through alpha n, and then I raise those to any power, z, so z is an integer here, from 0 all the way up to L plus 1 to the n, and then I can even take minus 1. So there's L plus 1 to the n of these numbers total. Right, there's L plus 1 to the n of them. And that's equal to, So again, we're doing some parameter counting, just like in the last talk. So there's L plus 1 to the n roots somehow, or equations I'm getting, that f of alpha 1 to the z all the way up to alpha, excuse me, all the way up to alpha n to the z, that this is 0. That's L plus 1 to the n equations. And that's also equal to the number of coefficients in my polynomial. Okay, because each lambda I can go from 0 to L, that's L plus 1 of them, and then there's n, so L plus 1 to the n. So it's equal to the number. So then I get some sort of matrix equation, and if I have a non-zero solution, then I get saying some determinant is 0. And so let's understand that determinant. So there are L plus 1 to the n numbers, alpha to the lambda. So I'm using the same multi-index notation as in the last talk, alpha 1 to the lambda 1, all the way up to alpha n to the lambda n. And now I consider the matrix whose rows are indexed just by my z's. So they go 0, 1, 2, dot, 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 and then all the way up to this L plus 1 to the n minus 1. And then the columns are indexed by sort of alpha to the lambdas for various lambdas, right? So all the n tuples lambda, right? There's L plus 1 to the n of those. So this is a square matrix. And in the matrix entry, I put alpha to the lambda z, right? So I put alpha to the lambda z. Okay. So the equation f of alpha 1 to the z dot 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 alpha of, f of alpha 1 to the z through alpha n to the z equals 0 is saying that if I take the column vector of p lambdas, that's saying that this is in the kernel, of this matrix. Okay, so for there to be a non-zero polynomial in the kernel, then that means that the determinant of this matrix has to be 0. But what is this matrix? This matrix is just a Vandermonde matrix, right? So these alpha to the lambdas, this is sort of supposed to be a prime. These alpha to the lambdas are some numbers. Okay, the numbers of a special form. That's okay, they're just numbers. And this is just a usual typical Vandermonde matrix. So when I first saw this, it was confusing. I thought it was some weird fancy Vandermonde, multi-parameter Vandermonde, but it's not. It's just a normal Vandermonde. Each alpha to the lambda is a number, and then I'm just raising it to the 0th power. So this first row here is just ones, right? And then the next row is just all of these alpha to the lambdas, and the next row is alpha to the 2 lambda, dot, dot, dot. So it's just a usual Vandermonde matrix. And of course, we know the determinant of the Vandermonde matrix is the, up to a sign, is the product of the differences of these entries that are indexing the things you're taking the power of. So we know that some alpha to the lambda equals some alpha to the lambda prime if the determinant is actually 0. So you set alpha to the lambda equals alpha to the lambda prime for some distinct lambda and lambda prime, and that means that alpha to lambda minus lambda prime is equal to 1. Okay, and that's what we wanted, right? So this is just the explanation of why it suffices to produce this auxiliary polynomial with many zeros, okay, where the vector alpha 1 to the alpha n, raise that entire vector to a power 0, 1, 2, 3, all the way up to some very large number, larger than the degree of the polynomial. If we can show that these are all 0, then we've gotten the required linear dependence over Q of the log of alpha I. Okay, have any questions about that? Okay. Okay, so how do we try to write down such a polynomial? So as I said, we're not going to be able to write down a polynomial with enough roots, but we're going to be able to write down a polynomial with at least a bunch of roots, maybe not quite enough, but that'll get us started. Okay, and the procedure to do this is just the pigeonhole principle. And this, as I mentioned, this is a lemma that goes back to Siegel, and I'm stating maybe a simplified version of it here that's good enough for our purposes. So we start with 2 parameters, n and m. So n is going to be the number of variables we have, and m is going to be the number of equations. So of course, if you want to ensure that there's a solution, just using parameter counting, you should hope that there's more variables than there are equations. So we have n is greater than, in fact, 2m. So again, there's this version of this where you just need m greater than m, but the statement becomes simplified if you let m be much larger than m, say n is larger than 2m. So we have this matrix of integers, which represents sort of coefficients in a linear system that we want to find a solution to. And we have a bound of h on the absolute value of the integers in this linear system. Then there is a solution to the linear system. So there's n variables, there are n parameters, integers that give me something in the kernel of this matrix A, such that each coordinate of B is bounded in absolute value by 2nh. Okay. And the proof again is just the pigeonhole principle. So you look at all possible image vectors of in z to the n with all their b's bounded by, say, nh. Forget put out take out, or I guess you say with absolute value nh, and you look at all possible image vectors. If you multiply a times b, you see what you get, and then by pigeonhole we're going to show that two of them have to be equal. So therefore, because it's a linear map, that means that there are differences in the kernel, right? So consider all vectors in z to the n with coordinates of absolute value at most nh. How many of those are there? There's 2nh numbers with absolute value less than or equal to nh. Okay, maybe up to a +1 here. I'm not going to worry about that. And it's in z to the n, so there's n of them, so you raise it to the nth power. Okay, how big is AB? So this is the dot product of a vector where each coordinate in the vector has size nh, and I'm multiplying them with coefficients that are size h, that's nh squared, and then I'm adding them all together, and there's n of them, so that gives me another factor of n. So the size of the absolute value of each coordinate is at most nh, the quantity squared, n squared h squared. Now, how many possible vectors are there? Well, there's right. So the image of this matrix is, right, it's going to be a vector of length m, because it's an m by n matrix. So it's going to be right. So the each coordinate has size at most nh squared in absolute value. So the number of such numbers is 2 times nh squared. Right. The number of integers of absolute value at most this is twice this. And then there's m such coordinates of the image vector. So it's that raised to the mth power. Okay. But now, right, so the number of what did I say? Right, so each coordinate has, right, but then how many vectors B are we plugging in? We're plugging in 2nh to the nth power, right? Because we're looking at all vectors of coordinates of absolute value nh, so there's 2nh of them, and there's n possible vectors, so it's 2nh to the nth power. And since we assume that n is greater than 2m, 2nh to the nth power is greater than 2nh to the 2mth power. So therefore, two vectors have to have the same image by the pigeonhole principle, and therefore their difference lies in the kernel. Okay, so that's Siegel's lemma. And so we're going to apply this to get our auxiliary polynomial that has a bunch of zeros. Okay, so let me just recalibrate this again. What do we have and what do we want? We're starting with an algebraic dependence, beta 1 of the log alpha I. So say beta 1 log alpha 1 through beta n log alpha n equals 0. We're going to rewrite this as just saying log alpha n equals beta 1 log alpha n plus beta n minus 1 log alpha n minus 1. So we're just going to rewrite one of the logarithms in terms of the other ones. It's always like, right, so at least one of these coefficients has to be non-zero, since it's a non-trivial linear dependence, you can divide by it. Okay, And recall what we want to do is we want to produce an auxiliary polynomial, sum of p lambda x to the lambda of some degree L, such that f of alpha to z is 0 for a bunch of z's, for z going all the way up to 0, from 0 to L plus 1 to the n. Okay. Now, as I said, Baker's insight is that we're not going to be able to prove, construct a polynomial right away with all that many zeros, but you can be clever and get a polynomial with some zeros, but also ensure that a bunch of its derivatives have zeros. And what do I mean by derivatives? If I multivariable polynomial, I mean derivatives with respect to this variable that I've been calling z, this exponent alpha to this z. So write this excuse me, this function, sum of p lambda alpha to the lambda evaluated at alpha to the z, write that as the function of z. Okay, and you can actually think of this as a complex analytic function of z by thinking of what does alpha to the lambda z mean. If z is a complex parameter, it would mean the exponential of z times lambda times some logarithm of alpha, right? And these are the logarithms that you you take the log. I said there's a choice of logarithm because logarithm is a multi-valued function. So you take the choice of logarithms that you started with in your linear dependence. You assumed you had a linear dependence. You take those logarithms. And then you use the fact that log alpha n, so this is where we're using the fact that we have our algebraic dependence. Use the fact that log alpha n can be written as a linear combination with algebraic coefficients beta of the log previous log alpha i's. Okay, so that's what we've done here in this next line. And right, so this is our function phi of z, and it's going to be just the derivative. When I say derivative, it's going to be the derivative of this one variable complex analytic function. Okay, we're going to want this. So saying that there's a bunch of z's such that phi of z is equal to 0, that's just saying f of alpha z is equal to 0, right? This is for if z is an integer, then this is just f of alpha to the z. So what we're going to want is not just that this is 0 for a bunch of integers z, but also that the derivative of this function, in fact, many derivatives of this function are 0 for a bunch of z. So that's going to make up for the fact that we can't just, from the start, produce enough zeros for the function that we want. Is we're going to give us something extra to make up for it, which is the vanishing of these derivatives. Okay, so now it's going to get a little bit technical, and so I don't necessarily expect people to follow every detail, but I put it in the slides so that I can make the slides available and people can really read a full proof if they want. But hopefully I'll convey enough of the flavor of it. So for every sufficiently large parameter h, we're going to choose our degree cleverly to be slightly less than h squared. And I just want to point out that it's our linear dependence of the alpha i's that's allowing this exponent to be less than 2. You always want to know where are you using the assumption when you prove a theorem to make sure that you're not making a mistake. This is where getting this exponent to be less than 2 is where you use your assumption that you have an algebraic linear dependence. Okay, so I'll just point that out right away. So it's h to the 2 minus something. And there exists coefficients. These are our p lambdas in our polynomial, and the bound on them is going to be e to the h cubed, such that not just does phi of z vanish, but the first m derivatives of phi vanish at all these integers z going from 0 to h, and a whole bunch more derivatives. In fact, there's more derivatives than values, right? So what I've said is that we're going to have a problem getting lots of values 0, but somehow you make up for it by getting a ton of derivatives 0, h squared.
Samit, could you just remind us, so L doesn't appear again in this theorem, but relates to the number of zeros, or?
Yes, it's the number, it's indexing the lambda. So really, right, so lambda 1 through lambda n are between 0 and L, right? And so this is the tuple. So there's p, there's L plus 1 to the n lambda p lambdas.
Great, thank you.
So the number of coefficients p lambda is L plus 1 to the n. That's what the L is. Okay, and those p lambdas are what are then used to define phi. So yeah, there's no connection between L and lambda and written in the theorem, but it's all sort of notation that hopefully one remembers. So phi of z, I'll just put it again. Phi of z is determined by the p lambdas by this function. So this is the definition of phi of z. It's defined to be this, okay? And so the indexing set is these lambdas here, right? So this is lambda is a tuple, lambda 1 through lambda n, where 0 is less than equal to lambda I is less than equal to L. Right. Does that make sense? Okay, sorry about that. Okay, so what is the mth derivative of phi? Well, okay, let's go back to phi. Let's go back. So how do you take the derivative? So this is actually, this is just derivative with respect to z. So oops, it's just the derivative with respect to z. So this is, so the derivative is just, you know how to take the derivative of e to the z times something, you take the something down, right? So we're just going to bring this down m times, right? So the derivative of phi of z is the same thing as phi of z, except there's this thing that's multiplying by z, and the exponent is coming down m times, right? Just with the lambda term multiplied by this thing, m times. And if you expand this out, right, this is a product of m things. If you multiply it out, then you get, we want to sort of highlight the algebraic parts of it. Okay, so we're using the algebraicity of the beta I. So you get a bunch of products of lambda I plus lambda n bi, okay, to raise to various powers, m1 through mn minus 1. Okay, and then you're going to get products of log alpha I stuff. And we're not going to be able to deal with that. So in order to get vanishing of the sum, it suffices to get the vanishing of each term in the sum. That is, for each tuple m1 through mn that m1 through mn minus 1 that add to m, we're going to get the vanishing of this value for all these z's. And that's going to imply that if you multiply these by the associated product of log alpha I, so I guess it would be log alpha 1 to the m1 times log alpha n log alpha n to the n minus 1, and then added those up over all the tuples, that's what's giving you phi m of z. And the only way we're going to know how to make phi m of z vanish is to get each of these individual algebraic terms vanishing, right? We're going to, because we're using this Siegel's lemma, where you, in fact, Siegel's lemma used integers, not just algebraic integers. We'll show in a moment how to get around that. But because we're using Siegel's lemma and this sort of pigeonhole principle, we wouldn't be able to deal with things like logarithms of these logarithms of these algebraic numbers. We can only deal with algebraic numbers themselves. So to get the vanishing phi m of z, it seems like we're doing something much stronger, which is we're writing phi m of z as a sum of algebraic numbers times some logarithms. We're going to say the only way we know how to make that vanish is to get all the algebraic numbers to vanish. So that's what we're going to do. Oops, sorry. Okay, so now I said you have to do something to go from algebraic numbers to integers. It's not just algebraic integers, but honest integers, right? Because that's how I stated my Siegel's lemma. And so here's a little trick, and this is actually somewhat standard in the field. So let D be the degree of the number field generated by all these algebraic numbers, alpha I and beta I. And so you can see we're really using the algebraicity here. You let Ci denote the leading coefficient in the integral minimal polynomial of alpha I. Then an easy induction shows that Ci times alpha I raised to the jth power can be written as a linear combination of just the first dth powers of alpha I. So alpha 1, so alpha 0, alpha to the 1, alpha all the way up to alpha I to the d minus 1 with some integer coefficients. That's the point, that these are now integers. So these integers then are going to show up in our sort of application to Siegel's lemma. Okay, and furthermore, you can bound the alpha I, js, these coefficients, and that's kind of why it's useful to put it in this form. You'll get an explicit bound on them. And I'll just state that later. This is an easy induction that anyone can sort of sit down and do, and I'm going to use di and bijs as the notation for the same thing for beta I. Okay. So now the expression. So the expression star is the expression that I wanted 2 slides ago. This is expression star. This thing where everything's algebraic now, right? These are integers. These are all algebraic. These are integers. These are algebraic. So everything is algebraic. Okay. So it will vanish. So here I've multiplied by a high enough power of, okay, so sorry, let me go back. I'll just tell you what I'm doing. I'm going to multiply this out, okay, expand this out with the binomial theorem, and then multiply all the terms together. Oops. And then I'm going to multiply by a large enough power of this CI. So CI, if I multiply by CI to the LZ, then somehow I get enough powers of CI that I can apply my previous result, that somehow I can write CI times alpha I to any power as an integer, honest integer, linear combination of the previous ones. Okay, so again, this is probably too hard to follow every detail of, but I wanted to put the precise statement. You can look back at it later and check that basically all I'm doing is saying that I can write the powers of CI alpha I in terms of a fixed set of, this is sort of these are the coefficients of, right? So this is sort of the coefficient of alpha I to the SI times beta J to the TJ. If I rewrite the previous expression in terms of these monomials with this range of S and T, using this inductive reduction hypothesis, where this reduction method, where I say every power of alpha I can be written as a some linear combination with integer coefficients of alpha to 0 to alpha to d minus 1, as long as I multiply it by a high enough power of CI. So that's what I've done. Okay, the whole point of this, right? So again, it's more important to understand this qualitatively than every aspect of the computation. Is the whole point of this trick is that we've used the monic integer polynomial of the alpha i's to rewrite the vanishing of the expression that we want as a linear expression of the p lambdas with coefficients that are integers. These are complicated integers, but they're integers and honest integers. Okay, that's the point of it. So it's exactly actually well, it's kind of like what we saw in the previous talk. You express the vanishing of a polynomial at a bunch of arguments as just being a linear condition on the coefficients. The only difference here is because I wanted to apply the Siegel's lemma, I wanted the coefficients to be integers. So I had to work a little bit hard to get them to be actual integers. Okay, and that other than that, it's just the sort of the first thing you would do is sort of to express the vanishing of a polynomial at arguments to be a linear system in the coefficients. Okay, and now you just check that you have all the bounds to make Siegel's lemmas work, and you can trust me that I did that. So we want vanishing for this many m's all the way up to h squared, and this many z's up to h. The number of such equations is going to be h squared to the n minus 1. So this is, I just want to point this out. So of all the things to gloss over, this is maybe one thing to actually concentrate on. Point is, this n minus 1 is very important. This n minus 1 is arising from the fact that we have n minus 1 m's, right? These are our m's. And what were the m's? Let's go back. The m came from expanding this out. And the point that we could reduce alpha n back to a linear combination of the previous alpha 1 through alpha n minus 1 meant that there were only n minus 1 m's instead of n m's. If we had log alpha n and we didn't have any relation with the previous alpha i's, I would have had n m's, and that would make all the numerology fall apart. So I just want to point that out because that's kind of the most important point where you're using your assumption. Okay, and so you work this out and you get, and the important thing here, this is basically just a constant, you can ignore it, but it's h to the 2n minus 1, and that minus 1 is very important, okay? All right, and then, so now we can see why our clever choice of L is going to be useful, because L plus 1 to the n is going to be h to the 2n minus a quarter, which is greater than h to the 2n minus 1, which is, all right, and so this number can be greater than twice this number as long as h is large enough. Okay, so that's very nice. And we want to bound the size of the coefficient. So I said in that induction where these algebraic integers satisfy these minimal polynomials with integer coefficients, then it gives you this inductive expression for their powers that you can see that there's a c depending only on the alpha I and beta I that bounds these coefficients as a power of c. And if you plug that all in, you can check, maybe it's not worth going through the details. If you plug that all in, you can check that, that the condition in Siegel's lemma is satisfied. So, so let's just look at this, for example, this expression, which showed up in our expression. So this is a constant, okay? And so as long as my k is bigger than or equal to ci is the leading coefficient of alpha I, so it can be viewed as a constant. So as long as k is bigger than ci, and remember, ai's, I said, these ai's grow as fast as a constant to the power of the middle index. And so it multiplies with this perfectly to cancel, and you get a constant to the LZ. Z is going up to h, so this is constant to the LH. Similarly, you can bound the other term. You get something slightly bigger because of this binomial coefficient. But long story short, if you multiply these two together, you still get something that's smaller than k to the h cubed. And that's where L, remember I pointed out earlier, h had to be h to the 2 minus something. And that minus something was very important. It's because you want it to be less than h cubed. And indeed, L is h to the 2 minus something. So this is all growing less than e to the h cubed. All right, and so you get the existence of these coefficients p lambda from Siegel's theorem. All right, so now we've gotten our initial polynomial, and I said if you check back on how many zeros it only has h zeros, but L was h squared, and I wanted h to the n. So I wanted h to the 2n zeros, and I only got h zeros. So I'm way less than I need to be. So how do I get more zeros using the vanishing of the derivative? So two ideas we're going to use in conjunction. So one is this basic principle that I want to explain now, which is how do you show that an algebraic number is 0? Well, it suffices to show that it's small enough. So the simplest form of this is the fact I mentioned earlier. If I have an honest integer and its absolute value is less than 1, then it has to be 0. Okay, let's make it a little bit more complicated. Let's say that I have a rational number, right? Because we're going to deal with algebraic numbers and not just algebraic integers. So if I have an algebraic number, well, if you have some bound on its denominator, if you know that d times your rational number is an integer, then you use the form 1. You say, okay, if absolute value of a is less than 1 over that bound, 1 over that denominator, then of course that says that absolute value of dA is less than 1. dA is an integer, so that means dA is 0, which means that a is 0. Okay, so that's form 2, slightly more complicated. And now let's do the full form that we need. Let's say that we're dealing with an algebraic number in general, and we have some bound on its denominator, so we know that we can clear its denominator with an integer d. So dA is an algebraic integer. That's what I mean by z bar here. And I know that it's small enough in some complex embedding, less than epsilon. And maybe I don't have such a good bound on the conjugates of this number. So the conjugates are all less than some m, okay? And it lies in a field of degree at most n over q, and epsilon times m to the n minus 1 times d to the n is less than 1, then a0. Why? Because this is sort of the norm of d alpha, right? Of dA, sorry. This number here is the norm from q of alpha down to q of, I keep saying alpha, sorry. I just called it a here. QA down to Q of dA, right? So if I take dA and then take all its conjugates and multiply them together, then the absolute value of that will be at most epsilon times what I get from all the other conjugates, so m to the n minus 1, then times d to the n, because each one has been multiplied by d. So if that's less than 1 and it's an integer, then it has to be 0, right? And if the norm of an algebraic number is 0, then the algebraic number is 0. Right. So that's how we're going to use this principle on how to get more zeros. Yes. So Hong asked, what is the size of epsilon? Yes, I mean, it's just notation, absolutely. I mean, maybe I put more notation on the slide than I needed to. So I don't really need epsilon. I can just say, I just put epsilon to indicate that that's what's really small, and the conjugates in general are going to be, so I could put absolute value of A here is what the point is that Hong was making, which is absolutely correct. The point of putting epsilon is just to tell you that how we're going to apply it is we're going to make one embedding small, like, right? So we're going to make absolute value of A small. And then the other conjugates, we're just going to have a kind of a weak upper bound, but the absolute value of A is going to be so small that when you multiply it by all the other conjugates, it's still going to be absolute value less than 1, so it has to be 0. If you're saying that if the norm is less than 1, then an algebraic integer is 0, yes. If the norm of an algebraic integer is absolute value less than 1, then the algebraic integer is 0, exactly. And this principle is only a restatement in a useful form. I mean, this principle is that statement. I'm just making that statement. Yeah. I'm just telling you how we're going to do it. Yeah, we're going to bound the algebraic number. We're going to get a bound on what denominator we need to, to clear the denominator, and then we're going to get a bound on all the other conjugates. That's how we're going to do it. Okay. All right, so the punchline is here. To show that an algebraic number is 0, it suffices to show that it is tiny and that its conjugates are not too big. Okay. So it looks like I'm pretty much out of time. Let me basically, just end with this slide. Okay, so and then we'll actually do this extrapolation, which is a little bit complicated. We'll do it next time. So I'm going to motivate the complex analytic, the complex analytic bounding of our values that we're going to then show must be 0 using the previous slide with the Schwarz's lemma. So this is something that we've probably all seen in a sort of a first course in a complex analysis. I have 60 minutes. I don't think I'm going to finish the proof even in 60 minutes. It was sort of intention. I realized that when I started the talk, so it makes more sense to end here, and then we'll be sort of a clean ending point, and then I'll pick up next time. So, is it really 60 minutes I'm supposed to speak, or 50 minutes? I thought it was 50 minutes.
You're very welcome to take 60 minutes, and we have half an hour always between talks. And in fact, in your case, you have like 22 hours till the next talk.
I see. Okay.
But you don't have to take them all. It's just available.
I see. I was confused. Okay, so maybe I will go on a little bit. If I'm expected to take 60 minutes, I'm happy to do so. I thought it was supposed to be 50. Okay. Schwarz's lemma says, so this is something from complex analysis, that if you have an entire function with a 0 of order t, say it's 0, then you get a very nice bound on the sort of the size or the growth of that function. So the absolute value of f, the maximum absolute value can achieve on the disk of radius r around the origin is little r over capital R to the power of t times whatever the maximum value it achieves on the disk of radius capital R. So let's, okay. So let's maybe draw a picture. We have capital R and we have lowercase r, and somehow what you get when you have a 0, which I'll draw with a really fat point here, that's sort of weighing things down by being, the function is really 0 there. It's not just 0, but a whole bunch of its derivatives are 0. Then that kind of pulls stuff down. And so sort of there's a bound on the value of the function on this disk given by the ratio of the radii to the power of t, the number of roots, times whatever the maximum value is on this outer disk. Well, I said on the outer disk. Of course, I put for anything inside the disk, but I mean, maybe I put a less than or equal to here. But of course, the maximum modulus principle tells you that the maximum is achieved on the boundary. Okay. So the punchline, maybe just read this, that roots of the derivative of a function can force good upper bounds. If these are strong enough at certain algebraic arguments, they can actually force the function to vanish. All right. So then we get more roots of the function, and maybe this works also for the derivative of the function, and more roots of its derivative, you get improved upper bounds, which then lead to more zeros. So you kind of, this is called extrapolation or bootstrapping. You kind of start with zeros, but also zeros of the derivative. Using the Schwarz's lemma, you get a bound, an upper bound on the size of the function complex analytically. It's so small that using the previous slide, the idea that algebraic integers can't be too small, otherwise they have to be zero, what you get is more zeros of the function. And then with those more zeros, then the Schwarz's lemma gives you even smaller value of the function. And you keep feeding it back into itself till you get more and more and more and more and more zeros until you get more zeros than you needed to apply your van der Waals trick and get the linear dependence you wanted. Okay. So I will, okay. So this is the more complicated version of the theorem that I just said, the Schwarz's lemma, that we're going to actually use. Again, another situation, it's a little bit complicated, so I don't expect you to follow every detail. So let's actually even just ignore this coefficient, this condition. This is just an inequality that we're going to need to make the proof work. But let me highlight what I think is important in this statement that you can see. Okay, so we're going to start with some bound. Okay, so this is going to sort of allow us to bound the absolute value of f on the disk of radius capital R is using this bound. Okay, but we're going to give ourselves a bunch of vanishing of a function, not just the function, but a bunch of its derivatives. So up to c derivatives at a bunch of points, 1 through a. Then what we're going to get is an upper bound on the value of the function for z going even further. I'm going to scale the number of points at which I have zeros. I'm going to scale that number times b and get at least, maybe not 0 yet, but because this is just complex and analytic argument, I'm going to get a really good upper bound on how small it has to be. And the point I want to make is that this upper bound is going to 0 faster than this is going to infinity. And that's going to be important. That is, there's an extra factor of some log a to the 1/2. So if a is really large, this is going to be bigger than this. And that's going to show up for us when we use that sort of algebraic integer argument I gave in the previous slide. This is kind of going to be our epsilon, and these are going to be our m's. Okay, that is, I'm going to bound one conjugate using this trick and say that it's really, really small. It's e to the negative something really big. And okay, the conjugates might be big, but they're bounded by something that even when I multiply by something like this, it's still going to 0. It's still going to be less than 1. And so when I multiply them together, it's going to be less than 1. Then if I say, oh, these are actually algebraic numbers, then it's going to have to vanish. Okay, so that's sort of what I want to point out, is this extra factor of log a to the 1/2 that's sitting there. Okay, so how does the proof work? So I thought I would go through the proof. Then again, I'm not sure if that's just a smart thing to do, but I wanted to give all the details of the proof. So we'll do this proof and then we'll end with, this is where we'll end with. And again, checking the inequalities is so important, but I think this slide is important. How do you prove the Schwarz's lemma? This is the same exact proof as the proof of Schwarz's lemma. So what you do is, and I apologize, I have a typo. I think I changed from G to F. Let's call this F. Okay, so we had a function F. So the fact that F and all of its derivatives up to the cth derivative vanish at the points 1, 2, 3, all the way up to A, implies that if I divide out by z minus 1 to the c times dot, 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 z minus a to the c, then I still get an entire function. Okay, so that's where the assumption of the derivatives all vanishing at these points gets used. So by the maximum modulus principle on the circle of radius a to the 1 plus epsilon times b around the origin, we have for all z of absolute value less than or equal to ab, we have that the absolute value of h of z is, of course, the absolute value of this entire function is achieved on the boundary. So it's less than or equal to maximum of the function on the boundary. So that's all we wrote. Okay, so now what can we say about this, about f, right? Well, what's the relation between f and h? The absolute value of f of z is just this constant absolute value. So now I'm thinking of z as a constant. Okay, so it's a particular constant inside this disk. Okay, so the absolute value of f of z is just the absolute value of h of z times this constant in the numerator here. Okay, and then so I'm gonna and then we just said that the absolute value of h of z is bounded by this by the maximum on the boundary of this large disk. So then I can write. So what is the absolute value of f of h of w on this disk? I break it up in terms of the absolute value of f of w and the denominator, so I can sort of combine this with this and compare. Okay. So now this we can bound just because this is on a disk of radius AB and this is on a disk, this W is on a disk of radius a to the what was it? A to the 1 plus epsilon times B. So that's why we use a sort of slightly larger disk. So that would allow us to bound this term. Okay, so if you're careful, you can bound the absolute value of this. So the biggest this could be is AB to the A. Okay, each term is absolute value AB bounded. And what's the smallest, this could be, you can see that it's bounded by this. And so you get an upper bound on what this ratio can be. And then for the first one, now for the bounding this is where you then use your assumption. Remember, one of our assumptions was a global bound on the growth of this function f of z. So you apply that right to this disk that w lies on. And our goal is to show that f of z is bounded by this. So then you just use the previous inequality. So we have a bound on this, we have a bound on this, you multiply it, and then somehow this is going to 0 faster than this is growing, and you get your nice kind of inequality. And again, I don't expect you to follow all the details of these two last things. Again, if you want the slides, I don't know if there's a way for me to make the slides available to everyone, but I'd like to do that. And then you can check these inequalities. So the punchline is, now that you see the proof, is you just define this function h of z to be entire, which is you take f of z and divide out by all these zeros that we have. You apply the maximum modulus principle, and that gives you an upper bound on what f of z can be. And when you choose your coefficients properly, satisfying some inequality, then you can in fact get the bound on f of z to look like this, which is kind of nice. It's going to 0 faster than these are going off to infinity. So that's what we're going to use next time. And so I think I'll stop here because it makes sense to get into the details at the end of the proof. But the idea of the end of the proof now is we have this function, we have a bunch of zeros and a bunch of zeros of its derivative. We apply the lemma that we just proved in order to get a bound on the derivative further out from the zeros that we constructed. We constructed, so in the notation of the lemma, we construct, if we start with a zeros of a function and its derivative, we then get a bound on the function going further out. And that bound is going to be so good that even when you multiply by all the other conjugates, the product is still less than 1. If it's an algebraic number, then it has to be 0. So then we're going to get a bunch of more zeros of the function. And in fact, the same argument is going to hold for maybe not all the derivatives, but at least half as many derivatives. And so we're going to get half as many derivatives getting way more zeros. And then we're going to keep doing it. And we're going to be able to do it enough times that we get as many zeros as we need. Okay, so I'll end there and we'll finish up the proof. And I'll give a whole summary of the whole proof next time so that it kind of